Dear students, starting with our new lecture series on organometallic reagents. This is our first lecture, and in this lecture, we will discuss what are the methods for the synthesis of organolithium reagents and their applications. As you know, the bond in case of organolithium compounds is a polarized carbon lithium bond, and here lithium is electropositive in comparison to carbon. So this will have a delta positive charge, whereas the carbon region will have delta negative charge, which is generally opposite to what we see in most of the organic halogen compounds, where carbon is having a electropositive charge and halogen is having electronegative charge, and this is opposite to what we have seen in case of carbon halogen compounds. So carbon lithium compounds, they will have lithium as less electronegative than the carbon. And likewise, these organolithium reagents, they are more reactive than Grignard reagent, that is organomagnesium halides, and that is why they are expected to behave both as nucleophiles as well as the bases. These organolithium compounds, they can be synthesized from the reaction of lithium metal with alkyl halides to give us alkyl lithiums, and lithium halide is formed as the byproduct. The reactivity of various types of alkyl halide in the formation of alkyl lithiums is that alkyl iodides, they are more reactive than alkyl bromides than alkyl chlorides, depending upon the polarity of the bond. Then there are some other methods also through which we can synthesize organolithium compounds. For example, we can synthesize these organolithium compounds by metal halogen exchange reactions. So when n-butyl lithium or secondary butyl lithium or tertiary butyl lithium, or in fact normal secondary or tertiary alkyl lithiums, they are reacted with different types of halogen derivatives. They will undergo metal halogen exchange reactions for the synthesis of alkyl lithiums. For example, in this aromatic system, 2,4,6 trimethyl bromobenzene, when this is reacted with n-butyl lithium, these two, they will undergo a metal halogen exchange reaction. So lithium will be exchanged with this bromide, and butyl bromide will be formed, and this organic compound will incorporate lithium in it, and we will get the aromatic lithium compound as the product. Similarly, in this heterocyclic bromide, uh, furane 3 bromofurane, when this is reacted with n-butyl lithium, again metal halogen exchange reaction, lithium will be exchanged with this bromine, bromidine, butyl bromide will be formed, and the corresponding lithium salt of lithium uh, compound of this furane will be. In addition, the compounds which contain acidic hydrogens, like this fluorine, these protons, because of the presence of these benzene rings, which are electron withdrawing in nature, these protons, they can be easily removed, and that is why these protons, they are called as acidic hydrogens. And these acidic hydrogens, they react with ethyl lithium, hydrogen from here, and ethyl, which is behaving as a nucleophile, because this is having negative charge and lithium is having positive charge. So this will abstract this acidic proton. Ethane will be formed, ethane gas, and this lithium will be exchanged with this proton, and we will get the organolithium compound as the product. So these are two very common methods for the synthesis of aromatic aryl lithium derivatives and these types of organolithium compounds. Then another method for synthesis of alkyl lithium is by replacement of a hydrogen by a lithium, and this process is known as lithiation. For example, 1-methoxynephthalene when reacted with n-butyl lithium. So the hydrogen present at this ortho position to this substituent will be replaced, and this H will react with the more electronegative butyl, and butane will be formed, whereas lithium will be replaced by this hydrogen, and we will get either 2 lithium or this 8 lithium as the 6 lithium as the product. Similarly, in these types of NN di-substituted benzamide, NN diethyl benzamide, when this is reacted with n-butyl lithium, then also this hydrogen at ortho position to this amide group is replaced by lithium. So a hydrogen is replaced by lithium, and we can say that lithiation process takes place in N and dialkylamides, arylamides also. And this reaction takes place in the presence of tetramethyl ethylene diamine, which is used as a base. And then this type of tertiary butylamide of this heterocyclic ring, pyridine ring, this also undergo lithiation at the ortho position when this is reacted with secondary butyl lithium. So this is another method by which we can prepare organolithium compounds. And these groups, they are very much needed for the ortho-lithiation of these aromatic systems, and the order of reactivities of these different groups is like this: sulfonyl imides, then sulfonyl aryls, N dialkylamide, oxazolines, then secondary amides, then thioamides, then tertiamines, ethers, NHAR, thioethers, and carboxylates. So these types of groups, they will help in ortholithiation of different aromatic things. So then reactions of different organolithium compounds. The most common reaction in case of organolithium compounds is reaction with carbonyl compounds, nitriles, epoxides, and their hydrolysis, reaction with carbon dioxide. So these are the common reactions which the alkyl lithiums they undergo. For example, when alkyl lithiums they are reacted with formaldehyde, we will get primary alcohols as the product. Similarly, alkyl lithiums on reaction with aldehydes, they will give us secondary alcohols as the product. Ketones, they will react with alkyl lithium to give us tertiary alcohols as the product. And you can see that the products formed in case of carbonyl system, they are same as we have seen during the reaction of Grignard reagent for with these types of substrate. Then in case of esters, we will first get the lithium derivative of the ester, and then that will undergo hydrolysis to give us ultimately ketones as the product. Similarly, nitriles, they will also react with alkyl lithiums to give us ketones as the products. Whereas addition of epoxides to alkyl lithium, they lead to the formation of primary alcohols or secondary alcohols depending upon the substitutions present at these two carbons of the epoxide. Then alkyl lithiums, they undergo hydrolysis to give us alkanes as the product. So H from water will get attached to more electronegative alkyl group, whereas lithium hydroxide will be formed in addition. Then carbon dioxide reacts with alkyl lithium to give us lithium carboxylates, and these lithium carboxylates, they will react with another molecule of alkyl lithium, which may be same or which may be different, to give us symmetrical or unsymmetrical ketones as the product. So these are some of the common reactions which take place in case of alkyl lithiums, and we will discuss these reactions in details one by one. First is reaction with carbonyl compounds. As I have told you, that organolithium compounds, they react with aldehydes, ketones and esters, and corresponding alcohols, they are formed as the product. And these alcohols, they may be primary, secondary or tertiary depending upon the type of carbonyl compound which is used during these reactions. You can see over here, if aldehydes, they are reacted with alkyl lithiums, they will give us secondary alcohols. Ketones, they will give us tertiary alcohols as the product. And in case of stereochemical reactions, the stereochemical addition will take place in such a way that the nucleophilic organolithium species attacks from the equatorial direction, and that is why we will get axial alcohol as the product in preference during the polar addition of alkyl lithiums to such type of ketones, which gave us stereochemical products. So there are two ways in which methyl lithium can add to this carbonyl. One is axial alcohol can be formed, other is equatorial alcohol. And as I have told you that preference is given that attack of the alkyl lithium takes place in such a way that a stereoselective reaction takes place, and the methyl group gets attached to the equatorial position and the alcohol formed is preferably axial alcohol. And you can see that when we are not adding any additive to this, 65% of the axial alcohol and 35% of the equatorial alcohol is formed. And this stereoselectivity can be improved if we add some lithium salts to this. For example, if we add lithium perchlorate, this can improve the stereoselectivity from 65% of the axial alcohol, it raises it to 92% of the axial alcohol. Then in case of sterically hindered ketones, as you have seen in case of Grignard reagent, here instead of addition, we get reduction of the carbonyl group in case of Grignard reagent. Whereas with alkyl lithium reagents, they do not reduce the ketone, but they add the alkyl halide, the organolithium compound adds to the carbonyl compound. For example, in this case, adamantone, when the reaction is done with Grignard reagent, ethyl magnesium chloride, then reduction of this ketone takes place. Instead of addition of this ethyl group, only reduction of ketone takes place to give us adamantole as the product. But when the same reaction is done with ethyl lithium, then addition of the ethyl group to uh, give us tertiary alcohols as the product. Whereas in this case, we are getting secondary alcohols as the product. So here we are getting the reduction product, whereas here we are getting the usual addition product with alkyl lithium. Then another example of sterically hindered ketone. Here also the tertiary lithium adds to the sterically hindered ketone to give us the corresponding tertiary alcohols as the product. Whereas in case of Grignard reagent, there is no addition, instead reduction of this carbonyl compound takes place. Then another example is this compound, the alkaloid of this type, uh, which is having ester moiety also, then this carboxy benzyl group also, and this heterocyclic ring also. So furan ring, ester, and this carboxy benzyl group. You can see the reaction is very selective in nature. This group is not affected, this group is not affected, only reaction takes place at the ester group, and as I have told you, esters, they are converted into the corresponding alcohols as the product. So methyl lithium adds to this ester group, and we will get tertiary alcohols as the product in 77% yield. Then another example is the enantioselective nucleophilic addition to this carbonyl compound. So this trifluoroketone reacts with lithium acetylide, and you can see that this ketone is a prochiral ketone. This can lead to the form of alcohol, which can be enantioselective nature. So, because though two isomers of the alcohol can be formed, and this reaction has been used in the synthesis of alpha-virenase, which is a potent HIV reverse transcriptase inhibitor. So when lithium acetylide is reacted with this prochiral ketone in presence of this additive organolithium compound, then a reduction of this ketone takes place to give us alcohols, enantioselective alcohols as the product, and further on reaction with different substrates, this can undergo cyclization to give us this biologically active HIV reverse transcriptase inhibitor, that is alpha-virenase as the product. Then enone substrates, they can also react with alkyl lithium compounds like thioanes, 1,3-thioanase, thioanase liquid, lithiums, and these organolithium compounds, they add to the enones in either 1,2 addition or 1,4 addition take place in such cases. So depending upon the reaction conditions, we will get either 1,4 product or 1,2 product. If we are using tetrahydrofuran only, then 1,2 addition product is formed in more than 99%. But if in addition we add hexamethyl phosphoramide, HMPA, two equivalents of this in DHF, then 95% of uh, the 1,4 product is formed. 95% of the uh, 1,4 product is formed, and you can see over here, in case of 1,2 addition, the alkyl group adds to the carbon of the carbonyl, and lithium adds to the oxygen. Whereas in case of the conditions when HMPA is used, then this R as a nucleophile will add to this carbon, and 1,4 addition will take place in such cases. Then some other examples is derivatives of carbonyl compounds like primary amides. They also react with alkyl lithium compounds. For example, three equivalents of butyl lithium, they react with these primary amides, and we will get these types of intermediates where three equivalents of lithium will add to these three position, and then this will undergo elimination of lithium oxide from here, and this monolithium nitrile will be formed, and this then undergo hydrolysis to give us nitriles as the product. So amides, they can be converted into nitriles using organolithium compounds. Similarly, we can use organolithium reagents in presence of dimethyl formamide, and at ortho position to these methoxy groups, we can have formylation to give us aldehydes as the product. Then carboxylic acids, they also react with organolithium reagent to give us ketones as the product of hydrolysis. So first, this will add to the carboxylic acid to give us these types of carboxylates, which on hydrolysis will give us ketones as the product. Then organolithium reagents, as I told you, they add to the epoxide to give us alcohols as the product. So depending upon the nature of the epoxide, we will get the type of enantioselective alcohol formation. And in these types of reactions, the organolithium compounds, they will attack the epoxide from the less hindered side of the epoxide or the substrate. Then organolithium compounds, they react with carbon dioxide to give us these types of carboxylate lithium intermediates, which will further add one more molecule of alkyl lithium or organolithium compound to give us dilithiates, and these dilithiates on hydrolysis will give us ketones as the product. So basically, carbon dioxide on addition to an organolithium compound will give us ketones as the product. Similarly, organolithium compounds, they can react with nitriles, aryl cyanides to give us ketones as the product. And in these types of reactions, intermediate imine salts, they are formed during the addition of the organolithium compound to the aryl nitrile, and these amine salts on hydrolysis will give us ketones as the product. Then general electrophilic displacement and nucleophilic displacement reactions, they are also undergone with the organolithium compounds. For example, organolithium compound will react with any alkyl halide to undergo metal halogen exchange reaction, which I have already told you during the preparation or synthesis of organolithium compound. So vinyl bromide can be transformed into vinyl lithium in this metal halogen exchange reaction, and otherwise it is very difficult to prepare these types of vinyl lithium compounds. But through this metal halogen exchange reaction, we can easily prepare these types of vinyl lithium compounds, which are very useful in organic synthesis. Similarly, the nucleophilic displacement reactions, they take place by SN2 mechanism. For example, when alkyl lithium will react with alkyl halide. Then nucleophilic substitution of the halide will take place, and nucleophile in this case will be the alkyl form. Whereas when the same reaction is done with aryl lithium, for example, this 1-chloro-naphthalene, when this is reacted with aryl lithium in presence of benzene, this will first undergo addition elimination reaction. H from here, Cl from here, and an intermediate benzyne will be formed. And this benzyne will react with aryl lithium in presence of protic solvent to give us these types of products by addition of the benzene ring. Lithium from here will this will be a lithium will be positive, this part will be negative. So this carbon ion will add to this carbon carbon triple bond either at this place or at this place. That is why we are getting either phenyl substitution at one carbon or two carbon of the naphthalene to give us two types of products. Then these aryl lithium compounds, they can also undergo a reaction with alpha beta unsaturated carbonyl compounds like this, and we can get either 1,2 or 1,4 addition in case of Grignard reagent. But when we react these with organolithium reagent, we will only get 1,2 addition product. So this is the advantage of organolithium compounds, that we will exclusively get 1,2 addition products when alpha beta unsaturated ketones, they are reacted with phenyl lithium to give us these types of alcohols. Then is ortho-lithiation reactions. As I have told you that the presence of some substituents on aryl group like NN di-substituted amines, uh, they will lead to the increase in the activity of the ortho positions, and N-butyl lithium will react with these types of substrate, and ortholithiation will take place, and these ortholithiation products formed, they can react with different organic compounds to give us different types of products. For example, this ortholithiation substrate will react with benzaldehyde, and the corresponding secondary alcohols, they will be formed on hydrolysis. The reaction takes place. This group helps in attack of the nucleophilic alkyl group with the removal of this ortho hydrogen to form the ortholithiation product. Similarly, these types of substituted amides, they will react with n-butyl lithium, ortholithiation will take place, and this will react with aryl halide to give us the corresponding alcohols as the product. Then lithiation of both N-phenyl and O-phenyl urethanes, that can also take place at the ortho position. For example, N-tertiary butoxycarbonyl aniline. So this one, N-tertiary butoxycarbonyl aniline, reacts with tertiary butyl lithium to give us this type of dilithiated intermediate, and this dilithiated intermediate will then react with aldehydes to give us these types of alcohols, and this tertiary butoxycarbonyl is a very good leaving group, and this will undergo cyclization to give us these types of biologically active heterocyclic compounds. Uh, or similarly, this dilithiated substrate form can react with aryl nitriles or phenyl isocyanate to give us these types of heterocyclic products after cyclization in quantitative yields. Then The lithiation of anthracite toxicarbonyl aniline derivatives, as you have seen previously with tertiary lithium and carbon dioxide. Here, the ortholithiation of this compound will take place at this position, and the corresponding carboxylic acid will be formed, and this carboxylic acid derivative which is formed is used in the synthesis of anthromycin, which is a very important drug which is being used these days. Then phenothiazines, they can also be reacted with carbon dioxide to give us these types of N-carboxylate lithiums. And these N-carboxylate lithiums, which are lithiated at the ortho position also, they will react with benzaldehyde or aryl halide to give us the corresponding alcohols as the product after hydrolysis. Then organolithium reagents, they also react with alkenes and alkynes to give us addition product in an intramolecular reaction. For example, if we take the example of this substrate 1,6-bromohex 1-anyl benzene, in presence of n-butyl lithium, this will undergo cyclization at this position and at this position to give us these types of products in 60% yield. So alkylidene cyclopentane will be formed in 60% yield. Then N-allyl N-benzyl 2-bromobenzamine. This reacts with tertiary butyl lithium in negative spartine to give us these types of ortholithiation intermediates, which undergo cyclization to give us these types of heterocyclic lithium compounds, and these on hydrolysis will give us 1 benzyl 3 methyl indolene in 87% anisomeric access. So we can have very pure anisotrophic products through these types of reactions. So these are the references which have been used for preparing this lecture. Thank you very much.